Greetings and welcome back. Today we'll be looking at polymerization reactions, or the reactions that form organic polymers. To put it simply, organic polymers can be divided into two groups. The first group is called Homo polymers, homo meaning same. Homo polymers have the same unit repeated over and over and over and over again. Copolymers involve multiple different units being repeated. And the simplest one by far is the homopolymers. They have the same thing over and over again. So we're going to look at that first, and then we'll move into the copolymers. Homopolymers in organic chemistry are almost always polymers made out of repeating units, multiple repeating units of alkenes, or C double bond Cs. No matter what's attached to the end of those, the way that we can polymerize that is attach those to each other, so that you have repeating units of those two carbons over and over and over again, or some large number of times. The way that we can connect those is in one of three different ways. Our first one is anionic, which involves an anion or a negative charge. Let's go with an OH minus. If you lined up a whole bunch of alkenes in a row, and for the sake of this, we're not going to worry about what's at the end of those four bonds attached to the alkene. Those determine exactly which polymer we make, but we'll get into more details of that later. But an OH minus has too many electrons. It can share electrons with that first alkene. Well, that would have to push some of these electrons out, and they could either stop right there, making a C minus, which is an anion as well, or they could just keep going and make a bond to the next alkene. Well, that would push electrons out, which would keep going to the next alkene, and that would push electrons out, which would keep going to the next alkene over and over and over again. And so the result of that would be that you'd have an OH attached to one subunit of something that was an alkene, attached to another subunit of something that used to be an alkene, attached to another subunit of something that used to be an alkene, etc., etc., etc. So you can see how these little subunits repeat over and over and over again, and therefore this polymer is just repeating units of those guys. Cationic polymerization pulls electrons backwards. So for instance, this might involve, let's make a C plus attached to 3 carbons. That would want to pull electrons towards it. So if you had a whole bunch of alkenes, all in a pretty little row, instead of pushing electrons like you would do with an anion, these guys would pull electrons. So this alkene would be attracted to your cation, and that would leave this carbon right here without enough electrons, which would pull electrons from the next alkene, which would leave this carbon without enough electrons, which would pull electrons from this alkene, etc., etc. That would end up with whatever your carbon was there, making a bond to something that used to be an alkane, or an alkene, attached to another subunit that used to be an alkene, attached to another subunit that used to be an alkene, attached to, etc., etc. And so once again, if we look at our brackets, we can see that there's repeating units of whatever this is. You might notice that this is exactly the same as what we have above, except for one difference, which is whatever is at the very, very end. Since these could be hundreds or thousands of repeating units, what is at the very, very end actually doesn't matter very much at all. All right, the third way we could do this, besides pushing electrons and pulling electrons, is a combination, which is using a free radical initiator. So, because we didn't get to use it last time, let's use AIBN. This could be done with a Cl radical, or of course peroxides can make O radicals. Any of those initiators we talked about last time would be fine. But you might remember that AIBN was, oops, that's nitrogen, is this thing, and it initiates by making at the center nitrogen molecule, and making 2 units that look like this. And that's just a free radical. So if we put that together with a bunch of alkenes in a row, Well, you may recall that what a radical wants to do is break up a stable, happy bond and steal an electron for itself. So it could steal one electron out of that pi bond, leaving another electron behind it. Either that electron could go over to this carbon, making that a radical, or really it's going to go out and look for another electron, which it can take from this pi bond, which would leave one behind, which would go out and find another radical, which would leave another one to go out, etc., etc. You'll notice that at the end of this, we're doing what we just did above, which is that we're making brand new bonds in between what was an alkene, which makes a brand new bond to something else that was an alkene, which makes a brand new bond to something that was an alkene. And it ends up looking like the exact same repeating subunit over and over again, this guy right here. And so overall, what you can see is that all of these are just this subunit here repeating n times. No matter which mechanism you use, they all just end up repeating over and over again that same 2-carbon chunk. And if you had, for instance, a benzene ring on one of these, and H's at all those other spots, you would end up with a polymer that, oh my goodness, that's ugly, that has a benzene ring there and an H at all of those other spots. And so what that would look like at the end of the day would be a benzene ring here and here and here, and so it would be at every other carbon. And that's in general how Homo polymers work. Let's do one example really quickly. Vinyl chloride looks like this. A vinyl is a C double bond C if you treat it as a substituent or name it as a substituent, but this is vinyl chloride right here. It's just that C double bond C alkene with a chlorine attached. In general, the way that we polymerize this is by that radical mechanism. This is vinyl chloride. And in the radical mechanism, if we were to start with a peroxide, we'll use a different example here, and we could add some light and split that guy in half, give us some O radicals. Those O radicals would go out looking for electrons from which or bonds from which they can steal one electron. So if we line up a bunch of vinyl chlorides in a row, that radical would preferentially, oops, just one electron there, take an electron away from this spot right here. And what that would make would be a brand new bond between the oxygen and, excuse me, this carbon right here, giving us carbon radical next to the chlorine. And so chlorine can inductively share electrons. They can make kind of a resonance structure there. But what we find is that it's more stable doing it that direction, and therefore the next one would want to line up as well so that it could make its radical next to the chlorine. And the next one would line up as well so that it could make its radical next to the chlorine. And these guys would polymerize just like we saw above. So if you do a bunch of these all at once, etc., we are going to make a chain that looks like RO attached to CH2, CCl, and then another bond to CH2, C with a Cl, and H, and then another bond to another one, etc., etc. We'll see that the repeating subunit is this guy, which came from our vinyl chloride. So drawing this out in a line angle structure, what you would see is that it would look like this, and then this, and this, and this, etc., etc. So your repeating subunit, once again, is the same thing. It's a carbon, it's a 2-carbon chunk. Every other one has a chlorine on it. And this would be called polyvinyl chloride, or PVC. So if you ever see that recycling code number 3, this is polyvinyl chloride, or PVC. All right, so that is it for homopolymers. They all go through one of those 3 mechanisms, and they all end up being repeating units of 2 carbons in a row that came from an alkene. So the second general group of organic polymers are copolymers. And these are things that, instead of being the same unit over and over and over again, like the previous one that was essentially A all the way through, these will often look something like A, B, etc., etc. And usually the way that we get these is by having something with a nucleophile on both ends and something with an electrophile on both ends. And so you would have a nucleophile and electrophile getting together and making a bond. And then you would have the electrophile plus the nucleophile of the next one making a bond. Nuke. And hopefully you can see that what would result from that would be repeating units of this guy, and then this guy and B, A and B, over and over and over again. All right, so I'm going to give you one example of this, and this is PET, or PETE. This is code number 1 for recycling. So this is in a lot of plastic bottles and like soda bottles and things like that. It's a really, really common polymer that we use, or plastic we use all the time. And it is a polyester, so it's repeating units of ester. So if you think about how we make esters, esters can come about in 2 different ways, well, 3 different ways, and they all come from making that bond right there. So either we could start with an alcohol and add, a carboxylic acid and add an alcohol, and those would get together and make an ester. Or we could start with an acid chloride and add an alcohol, which would make this bond. Or you could do transesterification, which is that you could start with one ester, let's say R double prime, and add in an alcohol. In all of these cases, the alcohol comes in, kicks electrons up, basically kicks that thing off, and you make a new bond there. Or the alcohol comes in, comes up, comes down, and kicks off the chlorine. Alcohol comes in, comes up, comes down, kicks off that guy. So you always have a leaving group, which defines your electrophile, and your alcohols usually end up being your nucleophiles. You can make polyamides as well, and that looks very similar, just instead of using an alcohol as your nucleophile. If we had a nitrogen as our nucleophile, we would make amides instead of esters. But this is what it would look like if you had esters. So notice that you would have to have something that was repeating units with 2 alcohols, one on each side. So in the case of PETE, or PET, we use ethylene, which has 2 alcohols attached, one on each side. So this would basically have a nucleophile over here and a nucleophile over there. And we'll normally react it with, I'm going to just give you the version of this that would come from an alcohol, or excuse me, carboxylic acid. And we use this guy, which is terephthalic acid. So in this case, these are our 2 electrophiles, is those carboxylic acids. So we could heat this up, and these guys would do Fischer esterification, where your alcohol right here would be your nucleophile. And we would lose that that hydrogen, we would lose this OH, and we would make a brand new bond in between that oxygen and that carbonyl, making ourselves a brand new ester. And that would just be if we did this one time. And so this is kind of our unit A right here, and this is our unit B right here. But to make a polymer, we would repeat that over and over and over again. So this might get a little tedious, but I will draw it out the best I can. We'll have a benzene ring here, followed by a carbonyl, and then an O with 2 carbons, and that came from our unit A. And then you would have another one of these guys. That's my unit B. And then I'd have my unit A again. and then I'd have my unit B again, and then I'd have my unit A again, etc., etc., etc. So this is really, at a molecular level, what all of your Coke bottles are made out of. Not metal Coke bottles, of course, but all your plastic Coke bottles or soda bottles. And so we can see that these are our units. Here is what we labeled our A, and here's what we labeled our B. But really, the unit that's repeating over and over again is kind of those two things put together. So the thing that repeats repeatedly, I know that sounds silly, but the thing that keeps going is this unit right here, which is A and B. So you've got A and B together, and then another A and B together, and then another A and B together, over and over and over again. And this can come from multiple different ways. You could use this alcohol right here. You could, of course, also use the acid chloride. We don't usually use the acid chlorides when we make polyesters, but it would give you a great yield. Or a lot of times, for the sake of making PETE, you would use like the methyl ester, which would be this guy. And any of these ways would work, because in all of these cases, you're just going to kick this part off. You're just going to kick this part off, and you're going to kick this part off. So you wouldn't see any evidence of your leaving group in your product, because it would be gone in any of those cases. So no matter which one of, so let's say this is A, any of these guys could be B, because we could just put them together again. So unlike those Homo polymers, the copolymers can always be broken up by hydrolysis. Hydrolysis will cleave an ester, and so it would just cleave the ester back. If you heated these guys in acid and water, and it would go back to being, in this case, an alcohol. But if you cleaved it by acid and water, you would always get the carboxylic acid again. All right, so that's how copolymers work. Let's try an example of this. And thank you very much. Please bring any questions you have to class.